What's up, guys? Welcome back. Episode 66. Yeah, exciting. Gonna do a few problems today. Oh, just want to check my mic. Yeah, gonna do a few problems today. Sorry. Yeah. Exciting. We're gonna get straight into it. So let's take a look at our Pokemon sound of the day. I think we're at Pokemon. Oh wait, maybe 66. My bad. So did I say 66? I don't know. We got a Machamp. A Machamp. Let's take a look at the Pokemon sound. Let's take a look. Oh, got a great ad.
Not at all.
Bro. There's that sound. There's probably people laughing at that right now, but there's that beautiful sound, that Machop sound. Pokemon 66. I just got to respond to this text really quick. Okay. Let's take a look. Sign into our Leetcode account. Got that +1 daily check-in. Gotta send those streaks real quick. I know I'm too old to be doing streaks, but I still do them. Just can never stop. That's okay. Yeah. Okay. Alright, let's take a look at some problems. Let's take a look at the problem that we missed yesterday. I'm not going to attempt this problem. I don't know, it is an easy problem. So let's check out this problem. So you get a list and we have to return it. Given an array num sort of non-descending order, return the maximum between the number of positive integers and the number of negative integers. Okay. There are 3 positive integers, 3 negative integers. The maximum count among them is 3. Okay. How is it 3? So we got 6 here in positive integers. And we got 2, 3, 4. I'm a little confused what's going on here. There are 4 positive integers and 0 negative integers. The maximum among them is 3, is 4. Okay, so I think we're just counting the number of integers. There are 2 positive integers, 3 negative integers. The maximum among them is 3. Okay, but 0 doesn't count. Okay. Okay, how... Okay. No, actually, I think we can easily do this. By nums. If I guess we want to make, well, let's make a pos and a neg. Loop through each of the numbers. If I is greater than 0, then pos plus or equal to 1. Else if I is less than 0, pos plus or equal to 1. Sorry, neg plus equal to 1. Else, I guess if it's equal to 0, then we can, I think we just skip this iteration, so we continue. And then we guess we just want to return the max of pos and neg. Okay. Is that it? Nice. Can we use binary search? It's a binary search problem. It says binary search, anyone tried that? Well, okay, that's one problem done. Interesting. Yeah. Let's take a look at our powerful study program. Gotta respond to this text though. Okay. Let's take a look. Yeah, no, notice heap is missing. Anyway, we got our binary trees. Let's take a look. Let's take a look at this one. Take a look at some searching algorithms. Construct a binary tree from pre-order and post-order. Increasing order search tree. Delete leads with the given value. Let's try this one. Delete trees. Give it a binary tree root and as your target, delete all the leaf nodes with target. Note that you delete a leaf node with value target if its parent node becomes a leaf node and has a value target, it should be deleted. Okay, wait. Note that once you delete a leaf node with value target, if its parent node becomes a leaf node, then... Okay, wait. I'm a little confused here. 1, 2... So we want to delete 2. So we delete 2 and 2. Okay, so I do know that we have to get to this value first and then probably move backwards, I think. The intuition doesn't really come to me in my head right now. What's kind of getting me freaking me out a little bit is kind of how you deal with, like, if maybe this is the node and then there's a 1 and a 2 here, how that restructures and everything. But I don't know, we're gonna to kind of think about this problem. 1325 delete leaves with a given value. Give me some hints. Give me some hints, please. Okay, I was right. We do have to start from the bottom of the tree, the post-order traversal. If a node is a leaf, both left and right children are null. So the bottom of the tree would be all the way to the left. So maybe while root is equal to root dot left. Okay, this gets far left. Right, so we get all the way to the left and then we want to pass in root, right? DFS root. Do we do the post order traversal outside of recursive function? Okay, if root we just return, right? Root dot left is equal to remove leaf nodes. Root dot right is equal to remove leaf nodes. Root dot right target. Alright. And then we do if root dot left, yeah. If root dot left and root dot right and root dot val is equal to target, then we make root equal to null, right? Root is equal to Oh, well, I forgot my return none here. Whoops. What are we getting here? Expected 1-3 null. Not root, if not root dot left, and not root dot right. I'm missing something. Remove leaf nodes is not defined. What is going on here? Oh my gosh, dude. Forgot to call self. Okay. Leaf node. If not root, return none. Let's kind of think about, I kind of want to think about the stack in this case, like what this kind of looks like. So I'll do it right here. Let's check out in this first test case. We have 1, 2, 3, 2, 4. I can't remember this over a bit. It's too much. 1, 2, 3, 2, 2, 4. Then we got our stack over here, right? So we're going to start off with our root here, right? Root dot left, if not root. So if this is nothing, we just return, but it's not. We have something, so we do root dot left, self dot remove those, right? So there we go. This goes onto the stack, right? So now we're in this case we called here, right? So it's not root, then we push it onto the stack, right? Boom, push it onto the stack. Then we have 2 again. Well, technically, yeah, we push it onto the stack, right? So then we push this one onto the stack. We got a 2 here. Oh wait, no, we don't push that one onto the stack because that's a leaf node technically, right? So we get here, right? And we see, well, no, actually we do, right? So we call root dot left here. Boom, root dot left. So we push this onto the stack. So now we're at this null node over here, right? We're at a null node here. And if not root, we return none. So this returns none, right? So boom, returns none back to this one, right? And then we check root dot right, right? So then we go down to this one here, right? This comes back, returns null, right? So then we get back here, right? And we realize this is a leaf node, right? This one here. So we do if not root dot left, if not root values exactly, we make this equal to none. So we make this equal to null, right? So then this is gone and returns, gets rid of this, goes back to 2 here, right? Instead, checks root.write, right? So we go here, realize this is null, returns back, right? And checks if its children are here, sets this to null, right? Processes this node, pops out off the stack, then we go to 1. Then we check root.write, right? So we go write, we go to 3. We check root.write, realize we have a 3 here. So this, couple this stays on the stack, right? Because then we check 3, right? Then we recall root.left, right? So we push the 2 onto the stack. Left, we got the 2 here now. Now we're at the 2. Then we do root.left on this one too. So we go here. See, this is null. We return null. Come back here, do the write. See, this is null. Then come back here to this 2. Check the children. See that it's null. Then we process this node, pop this from the stack. We come back to 3, check root.write. Right? Done with this. We're back here. We push. Now we're at 4. Right? We're checking, well, root. So then we have 4 onto the stack here. Right, and then we're checking root.left, realize this is null, process this node, pop this from the stack. Then we're at 3, we check its children. They're both null. They are both null, but the value does not equal. Oh no, sorry, this one has a child. So yeah, then we pop 3, right, process this node. And then we go back to 1 and we finally process, well, is this equal to target? No, it's not. So we keep it. So really, like, we return, our tree looks 1, 3, and then 4. This should be our returning tree right here, I believe. Yes, 1, 3, 4. There we go. That's kind of how our algorithm works. I'm going to kind of think about this problem in our way that we usually do it, where we create the DFS function, right? Because I think we should be able to do it, right? We call the DFS function with our root value, we pass in our node, and we do, well, if not node, we just return none, right? Then we do node.left is equal to DFS node.left, node.right is equal to DFS node.right. Right, and then we check, well, if node.left, okay, if not node.left and not node.right and node.val is equal to target, then we want to return none. And we want to just return our root, right? I think, oh sorry, our node. My bad. Return our node. I think maybe we need to return this. There we go. Should we do the iterative approach? The iterative approach would be hard with a stack. Because really... God damn it, dude. I think the iterative thing would be really tough. Let's take a look. I think we got a little buzzing noise going on with the microphone. Let's kind of turn it down a little bit. Yeah. I don't know. I don't know. It's right. It's whatever. Anyway, take a look at some Python solutions. What a Python 3 submission, bro, not a C submission. Oh, Python, here we go. Okay, let's take a look at a different problem. Binary tree tilt. Let's do increasing order search tree. Let's take a look at this one. Oh my gosh, dude. The root of binary tree, rearrange the tree in order so that the leftmost node in the tree is now the root of the tree, and every node has no left child and only one right child. Wow. Okay. What would be the best way to this? Would it be iterating over each value in this binary tree and adding it to a stack, sorting that, then creating a new tree node and looping over it? I don't know. I generally don't know. Let's do iterative DFS, right? So we create a stack. You put our root on it. I don't think it really matters. We only really need to loop with the root, right? While stack, our node is equal to stack.pop. And if node.left, we want to stack.append node.left. And then if node.right, we want to stack.append. Oops, sorry. Stack.append node.right. Okay, what we want to do with this node though is we want to append this to our little array. Right, let's organize this. We append here array.append node. dot val, right? We keep going through. Then after this, we just want to sort, right? So we do array dot sort. Then we want to add each value to a new tree node. Now I don't really know how to declare a new tree node, but I think it's like cur is equal to tree node. Something like that, right? And then we loop through for I in array. Cur dot right is equal to tree node I think. I think this is how you would do it. Let's check. This is how you do it. Okay, sorry. Dummy is equal to tree node. You make cur is equal to the dummy. For I in array, cur dot right is equal to tree node I. Okay, I did that right. Cur is equal to cur dot right. Then we want to return the dummy. Apparently dot right. Because it's an empty node at first, that's why we return right. There we go. Is that the fastest way to do it? Is that the only way to do it? Let's take a look. Because I don't know. Okay, they did the same thing as me. What did they do here? They did cursive in order to get our values to insert. Yeah, you can do it that too. That's cool, man. That's cool. That's cool. That's cool. Take a look at one more tree problem. Range sum of BST. Man, we still got so many more, dude. It's like it never ends, bro. Never ends. Let's do range sum of BST. Do a little bit of some BST. What are we doing here? Given the root node of binary search tree and edge is low and high, return the sum of values of all nodes with the value of the equals range low to high. I don't really understand. This problem's asking me, given the root, okay, node of a binary search tree and two integers low and high, return the sum of all nodes with a value in the inclusive range low to high. Oh, okay. So if they within that range, we loop through this tree. If they're within that range, then we add them and then we return. So in this case, we have 6 and 10. Okay. I understand. Okay, I think this is pretty straightforward to solve. Now here I think we can either do BFS or DFS. I don't think it really matters. Maybe let's do a BFS just because I want to. I feel like it's good to do both. From collections import DQ, right? Now let's make our queue here. So here we want to add Let's create our q is equal to dq root, right? And then we want to while q, we want to do for I in range length of the q, right? Here, I guess, I mean, we don't really need to take the range of the q, do we? Let's just do it anyway. Length is equal to the length of the q, right? Let's just put the length here, right? We loop through and we check, well, we want to pop. So let's do our q dot pop left, right? Let's make that our node. Node is equal to q dot pop left. What do we want to do when we pop the node? Well, we want to check the range, right? So we want to check, well, if node dot val is less than or equal to, sorry, if node dot val is greater than or equal to low, and node dot val is less than or equal to the high, then we want to append here. So let's create like some sort of res array or something. Make a list here, right? Oh, whoops. Then we want to do res.append node.val. Otherwise, we want to check, well, if node.left, do q.append node.left, and if node.right, we want to do q.append node.right. Then, well, we just want, I guess we just want to at each value we can do, well, and is equal to the sum of res, and we just return res, or return and, sorry. Runtime error, we have an invalid syntax, import click. I don't even know. From collections import DQ. There we go. Okay. A tree node is not iterable. Well, so like this or something. Okay. I'm curious. I'm gonna ask why. Okay. Okay. All right. Let's submit that. Nice, submitted. We're on the slower end a little bit, but what they do here, they did like, it's just like, what are they doing here? So is equal to list 0. Huh. That's a cool solution. My solution sucks. But it works. What do they do here? This is like a recursive function or something. Yeah, recursive function that tracks each node. They do DFS here. So they recursively do the left subtree, recursively do the right subtree, and then add the sums together at the end plus the current val. Okay. We've been doing a lot of trees recently. Let's take a look at some hash map problems. What do we got left? Prison cell. We got kth missing positive number. Let's take a look at this one. Given an array of positive integers sorted in increasing order in integer k, return the kth positive number that is missing from this array. I don't understand what this is trying to tell me to do. Less than over in complexity. Keep track of how many positive numbers are missing as you scan the array. 2, 3, 4. I'm confused, dude. I actually don't know what it's trying to get me to do. Positive number. Show code. Can you explain to me the problem? I don't understand. I don't really understand what it's trying to tell me. Given an array of positives, strictly increasing order and an integer k, return the kth positive integer. Oh, okay, wait. Kth positive integer that's missing from this array, but how? Why is it going up by 2? Okay, let's see this. Kth missing number in a sequence of positive integers. Understanding the problem. You're given a sorted array. Oh, okay. I understand. Okay. So in this case here, the 5th missing number would be 1, 2, 3, 4, 5, 6. We have 7, 8, and then 9 would be the missing one here. We're looking for the 6th missing number here, so looking for the 2nd missing number here, so in this case it would be 6. Okay, I understand. Trying to think, what's the best way to solve this problem? Well, I guess just like a normal loop, right? So we would do for I, we need to keep track of the indice plus the actual number. So we do, well, if I does not equal does not equal array I. Since this is a 0 index base, we have to start from 1. So let's go from 1 here to the length of the array. So if I it's not equal array, we want to make some sort of count here, right? Then we want to increment the count, right? So we increment the count plus equal to 1. Increase the count. Then we want to check, well, if count is equal to k, then we want to just return return array I, right? Always got this flu. We want to return return count if count is equal to k, else what do we return otherwise? Else 0. I don't know. Okay, let's get rid of this actually. Turn count. Print array I. Let's print. Hopefully that prints nothing. I'm not sure what prints nothing in Python. Okay. Taking a look at our first one here, we check, well, we have 1. Okay. Hang on. I see. I think we're messing up the thing here. So I guess we're going to have to make some sort of like tracking is equal to 1, right? And we have to do, well, if tracking does not equal I, count plus equal to 1, and we have to increment tracking after each loop. Tracking plus equal to 1. Then we want to return our count. Let's see. Print tracking. One, two, two, three, 3, 4. Okay, wait. Oh, wait, that's not, this isn't gonna work. Yeah, this is not gonna work. What is the way to do this then? Got a little update on my machine here. Little Windows update. Yeah, no, that's not gonna work. Binary search. I want to think about this differently. I guess we need to keep track of the length, right? So the length is equal to the length of the array. Right, and we can check, well, fine, range length. Starting from 1. Let's convert array into a set. If I not in res, let me increase our count. Right. Okay. Okay. Yeah, I don't think this will work either. I don't think this will work either. Too many edge cases. Trying to think. Man. What is the way to go about this problem? I'm gonna ask for a hint. Can I get a hint? This hint just says, well, loop over all the numbers. Simulate the counting missing numbers. Start from 1, the first positive integer. Keep track of how many numbers are missing while iterating through array. Oh, it's because we're going to the length of the array. We want to go to the max number. Length is equal to the max of array. This should be better. Count is equal to k. Then and return I. Okay, this one passes, right? But then we have an edge case here if we get to the end, right? Else. Plus k. There's no way this works, bro. Like, there's no way this submits, bro. Like, no shot. Oh my god, it's actually pretty close, dude. No way. Okay. Why is this not printing 1? I don't understand. Oh. Return count if There needs to be a better return here, dude. I just don't know what it would be like. I don't know what this return here would be. I really don't. I'm gonna have to ask. Okay, so that's what it is. We return the max of the array plus k minus count. I just couldn't figure out what it was, dude. There we go. Honestly, the better solution is the binary search. Ah, bless me, dude. What is the slowest solution, bro? Oh, no way, bro. What a solution here. If I in range 1 to 1,000, if I not an array, k minus equal to 1, k is equal to 0, return I. Nice. Okay. I'm gonna try the binary search solution because I'm curious. Okay. Let's try the binary search solution. I is equal to 0. J is equal to, I guess what? The max of the array. I don't know if the max here would be the max plus the k for the j here, or it would be the length of the array, the end index. Okay. Okay. Search for the first index I with a number of missing elements before. Okay. Okay, so while I is less than or equal to j, we want to check, well, calculate mid, which is I think it would be different here. Calculate how many missing numbers are missing before array mid using the formula missing count is equal to array mid. How many numbers are missing? Okay. Mission count is equal to array mid. I think we're gonna have to sort our mid here, but we do. What is it again? I think it's like mid is equal to high minus low plus low over 2, something like that, I think. I don't know if this is correct though. Can't mess it up. This needs to be over here. I don't really get it, but it says here, search in the XI when the number of missing elements for array I is at least K. If missing count is less than K, I is equal to mid plus 1. To be honest, else J is equal to mid minus 1. This is confusing, bro. Like, we're getting the array mid minus mid plus 1. How does that? How the hell is that? I think so. Okay, let's like kind of look at this on Paint. Curious how this works. So if our thing is 2, 3, 4, 7, 11, right? Whoops. 2, 3, 4, 7, and 11. Okay, and our K is 5. Mid is equal to low plus high. So our low is 0. Our high is the length of the array minus 1. So 1, 2, 3, 4, 5. Right? High is 5. Midpoint, which is high minus low 5 plus low 5 over 2, 2.5. Okay, so our midpoint is 2, right? Fuck. Mid plus 1 is equal to 4, high is equal to 4. Alright, bro. This is a little confusing, honestly. It's optimized solution. We're gonna come back to it because, man, it's too much involved with this. But array high minus high, like, look at this return here, bro. Like, what is going on here? High plus 1 if high is greater than or equal to 0, else k. Oh, jeez, bro. Oh, jeez. Low, high, low is less than high. I mean, whoops. High is equal to mid minus 1. I definitely need to do some binary search problems, dude. Like, I definitely messed something up here. There we go. Okay. We'll come back to that. That was little. I'm not really a pro of binary search, and maybe after a few more binary search problems, I'd understand it better. I don't really know. I don't know. What is this? Given 3 integers x, y, and bound, return a list of all powerful integers that have value less than or equal to bound. An integer is powerful, it can be presented as. Two 0 plus 3 0. Alright, we're going to come back to this problem. This is kind of a weird problem. I don't really understand this either, to be honest, because it's like integers powerfully can be presented as xi plus yj. Plus yj. Oh, okay, I understand. Right, so this is our x and our 2. We can do everything up to that. You can see how our x here only goes up to... to... Okay. We're going to solve this problem, but then I think we're going to call it there and maybe do some binary search tomorrow. You're one person online. Is that me doing this problem? I don't know. Okay, we're going to need some hints here. Give me some hints. 970, powerful integers. See, I don't really understand the problem. I think that's where it's given I, x and I in a bound. You need to find all numbers z is equal to xi plus yj. He's equal to... Okay, let's use a hashy to store our values. I think we're going to need 2 loops for I in range. For j in range. Range y. Let's do our bound. Maybe it should be the bound. I don't know. So I think x here. You can do num1 is equal to x to the power of I. Then num2 is equal to x to the power of j. If num1 plus num2 less than bound, It's less than or equal to bound. And set dot add num1 plus num2. And we just return our set. Numbers to set in Python. Is it set.add, dude? Isn't it right? Yeah. Can't apply int object. Okay. Num1. Num2. Let's add and here. There we go. What is going on here, bro? Descriptor for add for set objects don't apply to an int object. I don't understand. Oh wait, return. Oh my gosh, dude. Hashy. I think we have to cast it into a list here. Okay, so one thing is we forgot. Okay, it's this instead. If num1 is less than bound, oops, I meant if it's greater than the bound. Okay, I guess total's a better keyword for this. We will close total is equal to this, and we would append total. That's not equal to bound. Maybe we have to hard code 100 into here. I don't know what's wrong here. Oh shit. Whoops. Okay. we go. Cool. I mean, we had pretty much the same solution. I mean, when I asked for help, like, ours would have worked if we just... I mean, this was my original solution over here, right? I think if we just did this, it would have worked. I think these have to be a little bigger. It's not getting all the values, maybe. No. I don't know. What is wrong here? I generally don't know. Oh my gosh, dude. Whoops. There's our other one. Eight of 104. The range of this 100. Okay. It's the fastest solution. Double for loop. It's an interesting way to think about it too. Okay. Alright, well, I'm gonna call it there. I appreciate you guys watching today. I will see you tomorrow.